Today we're going to talk about position, velocity, and acceleration. This is really one of the most accessible applications for derivatives. We'll talk more about how these things relate as far as derivatives, but we're going to start by just reminding you that derivatives, slope, and rate of change are all connected to each other. So the first example we want to look at, it says you travel 6 miles in 12 minutes. What was your average rate of change? Now we typically talk about miles per hour instead of miles per minute, so that's why I have the 1/5 in parentheses after the 12 minutes, because that's 1/5 of an hour. So you travel 6 miles in 1/5 of an hour. What was your average rate of change? Well, if you think about it, if it takes you 1/5 of an hour to go 6 miles, then you can go 5 times that length in 1 hour, so it would be a total of 30 miles per hour. Now there's lots of different ways you can approach this, but what I want to show you is that you're essentially, whether you actually use it or not, you're essentially doing the slope formula with this. Here's what I mean. You're starting at time 0 and you've gone 0 miles. And then 1/5 of an hour later, you have gone 6 miles. If you simply do the slope formula, you get 30 miles an hour. Anytime you're asked to do the average rate of change, or the average velocity, or the average of any kind over an interval of time, you're going to use the slope formula. So there's no calculus involved here. It's just old school slope formula anytime they ask for the average rate of change or average velocity over an interval of time. So let's look at this example. A billiard ball, that's like a pool ball, like a cue ball or an 8-ball or thing like that. A billiard ball is dropped. Its position function is s of t equals negative 16t squared plus 100. What is the average rate of change from time 1 to time 2? So again, we're asked to find an average rate of change, and we're doing so over an interval of time from time 1 to time 2. To do this, we need to use the slope formula. That means we need ordered pairs. So let's plug 1 in. We get 84. We plug 2 in. Let's see, 2 squared is 4 times negative 16. I believe you get 36. Then we do the slope formula. 36 minus 84 over 2 minus 1. That's negative 48 over 1. So it's negative 48, and I know I didn't specify this earlier, but this would be feet per second. So the billiard ball is falling at an average rate of negative 48 feet per second over the interval 1 second to 2 seconds after it's dropped. Now, some of you may be wondering, why is it negative? That may seem really strange that you'd be going negative velocity. Just think of that as a direction. All the negative is doing is letting you know you're falling down. So anytime an object is moving downward or backward, we call it a negative velocity. So again, that's just to help specify a direction, is all that negative means. So let's contrast that with this question. Actually, this should say velocity. Let's fix that. This gives the same formula, so we're still talking about the billiard ball that's falling, but it says what is the ball's velocity at time 1 and at time 2? So I'm not being asked for the average rate of change over that interval of time. I'm being asked for the instantaneous rate of change at specific moments. This is when you want to use the derivative. So average rate of change over an interval of time, you use the slope formula. Instantaneous rate of change at a single point, you want to use the derivative. So I take the derivative of my equation, and I get negative 32t. And to find out what the velocity was at time 1, I just plug time 1 into the derivative. So it was negative 32 feet per second when exactly 1 second had passed. And then when exactly 2 seconds had passed, it was going negative 64 feet per second. So that's how you accomplish it when you're looking for the instantaneous rate of change or the instantaneous velocity at specific moments in time. So let's talk about these position functions. We've been using position functions so far in this lesson relating to gravity. We're going to stick with that today. If you're in my course, you don't have to memorize these as much as just recognize them and know that the negative 16 in front implies feet and the negative 4.9 in front implies meters. You also need to know what these mean. This is V with a little subscript with a 0, and that is said V naught. Just so you know, that's not N-O-T, but N-O-U-G-H-T. If you've ever heard someone saying that was all for naught, or I think somebody said some video games with cars talk about going from naught to 60, it's just another word for nothing or zero. So V naught means the initial velocity. It's telling you what the velocity was at time 0. So your velocity will likely change over time. This is simply representing what the velocity was at time 0. So that doesn't change. It was just one specific velocity at time 0. Same with your position. Your position changes over time, but this S naught represents your initial position, so the position at the beginning or the starting point. So V naught is your initial velocity, S naught is your initial position. And I mentioned at the very beginning of this, we talk about how position, velocity, and acceleration are related to each other. Well, it turns out that if position is your original function, then the velocity is your first derivative. And the acceleration is the second derivative. And if you relate this to rate of change, that should help you make sense of this. Velocity tells you how quickly your position is changing. Acceleration tells you how quickly your velocity is changing. So velocity is the rate of change for the position, meaning its derivative. Acceleration is the rate of change for the velocity, meaning its derivative. So it goes PVA. Position is the original, velocity is the first derivative, and acceleration is the second derivative. So let's apply this to this problem. A diver jumps from a platform 32 feet above the water. His position function is given by S of t equals negative 16t squared plus 16t plus 32. And the first question they ask is, when does the diver hit the water? Okay, so you need to think very carefully whenever you ask these questions about what this means mathematically, or what this means as far as numbers are concerned. So at the moment the diver hits the water, he first makes contact with the water, hopefully with his hands if he's done it correctly. You got to think, what does that mean as far as numbers are concerned? Well, it would mean his position is now 0. So we have a position of 0. So to solve A, we would plug 0 in for the position. And now we can factor this and solve for t. Notice I factored out a negative 16. That way it would change my squared to a positive term. That's my preference anyway. Easier to factor. We get t minus 1, t plus 1, t minus 2. If we set that equal to 0, we get times of negative 1 and positive 2. Now we are not able to travel back in time, so we will not be using any negative times. So you can throw that one out, and you know that he hits the water exactly 2 seconds after he jumps. So that's our answer for part A. Now part B, what is his velocity at impact? Well, velocity is the derivative of the position function. So if you go back to the position function, we can take its derivative. You can call it s prime of t, or you can call it v of t, because it's the same thing. Either one of those. And we take the derivative, we get negative 32t plus 16. And we want to know what it is at impact. Well, we need to plug in a time. Hey, luckily A just asked us to find that. In A, we found out that the time of impact was at 2 seconds. So we plug in 2 seconds. We get negative 64 plus 16. So we again get negative 48 feet per second. So it took him 2 seconds to hit the water, and at the moment he hit the water, he had a speed of negative 48 feet per second. Last example. A student hawked a loogie off a clock tower. It took 3.5 seconds for the loogie to hit the ground. How tall is the tower? So forgive me for the crude example, just was meant for some laughs. It took 3.5 seconds for the loogie to hit the ground. First of all, some of you may be thinking like, well, things fall at different rates. And that is true, but it is only true because of air resistance. And just to simplify things, we're not going to worry about air resistance. So just a fun fact, if you have no air, very little air, things actually fall at the same speed. A feather and a bowling ball would fall at the exact same speed if there was no air. Air resistance is the only thing that causes things to fall at different rates. Gravity pulls the same on everything. So let's start by making a position function. We know the general position function looks like this. Just for simplicity, we're going to say that this loogie is dropped from the person's mouth. And when things are dropped, their initial velocity is 0. It's not being thrown up, it's not being thrown down with any extra force. If anything is being dropped, it has an initial velocity of 0. Now we don't know the initial position. That's what we're looking for, because the height of the tower would be the initial position. If you look back at our example with the diver, he was 32 feet above the ground, hence he was 32 feet as his initial position. So here we're actually trying to solve for S naught. Well, let's simplify this a little bit because we know we don't need that middle term because 0 times t is just 0. So I just end up with this for my position function. So we know after 3.5 seconds the loogie hit the ground. So at 3.5 seconds he hit the ground, meaning his position was then 0. So now we can just solve this for S naught, and we find out that the height of the tower, which is also the initial position, was 196 feet.